Hi folks, Mr. Long here. This is our third and final example in graphing logarithmic functions. So what function are we going to graph this time? Whoops, this one here. And this is an interesting one because it's got a reflection, it's base 5 rather than base 10, and it's a pretty complex function if you look at it. Plus there's a coefficient in front of the log. So there's a lot of stuff going on here. So first things first, let's identify any reflections. Okay, has y been replaced by negative y? Well, the coefficient there is 4, not negative 4, right? So I can't multiply by a negative and make the left side negative. But look at x. Is x being multiplied by a negative? Yes, it is. So that, folks, is a horizontal reflection. We've replaced this x here with negative x over here, right? So the basic graph that the basic shape of the graph we're looking at is this one. It's reflected horizontally or over the y-axis. All right, the evaluated power and the domain. Okay, so we know that inside the domain, inside the log is this, negative x over 25. That's our evaluated power. Well, that always has to be greater than 0. Now, excuse me, I can multiply both sides here by 25, negative 25, right? So that will give me negative 25 multiplied by negative x over 25, and then I have 0 multiplied by negative 25. Well, something that we've learned is that when we multiply by a negative in an inequality, we switch the inequality signs. Why do we do that? Well, let's just take a specific example. Is 3 greater than negative 1? Yeah, for sure it is. What if you multiply by negative 1? Well, then you get negative 3 and positive 1 over here. Well, is negative 3 still greater than positive 1? No, I have to switch the sign. Okay, so if you multiply by a negative or divide by a negative, you have to switch the signs. All right, so then that divides out, the negatives divide out, and we have x must be less than 0. And that, folks, is our domain. But you know what? We knew that anyway. Look at this. We knew it was a horizontal reflection. Okay, so x is always going to the left of x equals 0. Okay, that's the domain, but it also tells us that our vertical asymptote is at x equals 0. So now we know our vertical asymptote and the direction of opening. Excuse me. So, now what we're going to do is simplify the function. So remember horizontal scaling factor, you might call horizontal compression or stretch. So this requires our log rules. And this one is going to be our log of, remember that the log of a over b equals log a minus log of b. Okay, and why is that? Well, this right here is an evaluated power. Okay, those are powers. And when you divide powers, you subtract the exponents. Logarithms are exponents. Okay, so for this one, how will I do this? Well, it's going to be 4 log of negative x minus 4 log 25 plus 12, right? Because the 4 is multiplying in. So it's 4 multiplied by all of that, right? So that's why we have the 4 in front of both of those. So this is 4 log of negative x base 5. But what is this worth? Well, 25 is nothing more than 5 squared. So what exponent do I put on 5 to make 5 squared? 2. 4 times 2 is 8. Minus 8 plus 12. So we end up with 4 log negative x base 5 plus 4. That's our simplified form. That's a nicer form to work with. And again, you can use either form when you solve for the x-intercept. I think another time I did the original one. This time I'll do the simplified version. Again, it doesn't matter which one you work with. There's reasons to use both. One reason you want to use the original is because you know you haven't made a mistake. But one reason you want to use the simplified version is It's simpler. So I might encourage you, if you're very confident, use the simplified version. Okay, so let's go ahead and do this. How are we going to solve this equation? Well, the first thing I'm going to do is subtract 4 off both sides. That gets rid of that. And then what I'm going to do is to divide by 4 to get rid of that. So what will that leave me with? Log of negative x base 5 will equal negative 1. Okay, log of negative x equals negative 1. So again, what is this? This is the base, this is the evaluated power, and this, folks, is the exponent. How do I isolate for that? I think you know. Negative x will equal the base 5 to the exponent negative 1, or x equals negative 5 to the negative 1. I multiplied both sides by negative 1. And what does that mean? Negative exponents mean division. How many times? 1. Divide by 5 once. So x equals negative 1/5. And that, folks, is our x-intercept. Okay, so now I can draw our sketch. So our sketch, I've sort of already got it drawn here. So the x value here is negative 1/5. The vertical asymptote, we know, is x equals 0. And the graph opens to the left. What I'm left with is to verify the y values close to the vertical asymptote and at the end behavior. So we want to verify the direction of the vertical asymptote. So we know the y value here had better be negative. Let's take a look and see if it is. So it opens to the left, right? Okay, so I know the vertical asymptote is at 0. To go to the left by 5 to the negative 4th, which is not a very big distance, I need to subtract. Okay, so remember in here we had our argument was negative x. We call that argument, the thing inside the brackets, the evaluated power. So that's going to become the negative of negative 5 to the negative 4, right? Negative x. So a negative times a negative is a positive, right? So that makes that positive. And then what is this then worth? What exponent do I put on 5 to make 5 to the negative 4th? Negative 4, right? Negative 4. So that's going to become 4 multiplied by negative 4 plus 4. And what does that work out to? Negative 16 plus 4 is negative 12. Oh, look at that. So at this point here, I know the ordered pair is negative 5 to the negative 4 and negative 12. Does that seem reasonable? Yeah, for sure it does, right? Because that means this distance here to here is negative 12, because it's got to be below the x-axis, and that's reasonable. All right, now let's check the end behavior. Now this time, the vertical asymptote is 0, and then I'm going to go to the left 5 to the 4th units. So 5 to the 4th is 625. So up here, what I'm doing is, this right here is 625 units to the left, right? So 625 units to the left of that vertical asymptote. That should give us our end behavior. Okay, so again, the formula in here was negative x in the simplified version. So that's going to be the negative of negative 5 to the 4th. Well, a negative times a negative is a positive. And then this right here becomes, what is that? That is, what exponent do I put on 5 to make 5 to the 4th? Well, it's 4. So that's going to equal 4 multiplied by 4 from this plus 4. And so 4 times 4 is 16 plus 4 is 20. So I go way up here, and I know that the ordered pair here is 5 to the 4th, comma, 20. So that means that distance from there to there is 20. Okay, so that works perfectly. Our graph is verified. Okay. So again, I encourage you to go over this again. these steps, this organizer will be provided on any evaluations that you have, because I think it's important to be able to have a structure. It's not often that I'm very focused on following a particular algorithm, but I think for graphing log functions, it is very helpful to do it this way. Okay, so again, rewind, watch it over again, make sure you understand it, and then attempt the homework. Good luck. Have a good day.